could be pockets of gas. So in the ionosphere, you could have pockets of ionized gas and get scatter off that. So anything that causes effectively a reflection of an object we call scatter. So the difference between a reflection and scatter is reflection really is off a smooth surface where it's sort of like looking in a mirror. You get, you can see, you can see a reflected image in effect. Where scatter is, you've got a lot of light going in a lot of different directions. If I put my hand across the lens there, you can see, well, I can see it's illuminating the front of the projector here. It becomes very bright because, and it's not a reflection, but it's scattering of the light off my hand. It's illuminating this side of the projector. So that's scatter. Okay, so when we have scatter, I don't know if it's in this slide, but the scatter occurs in different directions. So when the radio wave hits the object, it's going in all directions. So some of it's going forward, some of it's going to the side, some of it's going in the back. So I think there is a question about forward scatter, back scatter, and so on. Oh, there's the animation. Let's do that again, because that was good. So you've got the radio wave, goes up, hits that set of objects, and then goes off in all directions. Okay, yeah, so we've got rain, we can scatter off rain, ice pellets. There is an effect, I don't know much about this, trans-equatorial scatter, which I think is a tropical or tropospheric effect. And then we've got things like aircraft scatter, and we've got yeah. So actually, the chaff is where you actually release things into the atmosphere to cause scatter. This is used by the military if they've got an aircraft and somebody's firing a missile at it and it's homing in on the aircraft. They will actually not an aircraft, maybe a battleship. If you've got a battleship, somebody's going to fire a missile at it. You throw out chaff, which are little particles, into the air around the ship that now looks like a bigger target than the battleship. So the missile goes and homes in on the chaff. Meteor scatter. So we get some times of the year we get a lot of meteors hitting the Earth. Can't remember the names of any meteor showers, but as the meteor hits the atmosphere, it creates intense heat and ionization, and we can reflect signals off the meteors. So people like to try doing things like that. Lightning is another one, where the lightning can create little areas of ionization, and again we can reflect off that. So some people like to experiment and try all these things. Dave talked last time about beacons, and I think I showed you this chart showing the beacons on 10 meters, and you can see if you hear those. So right now at this time in our sunspot cycle, basically you don't stand a chance of hearing any of those. One thing I like to play with as a propagation tool is it's called WhisperNet, which is Weak Signal Propagation Reporter, I think. And what I do is, or what people do is they set up beacons. So the idea of a beacon is you're not actually talking to anyone or sending Morse code or anything like that, but you just have a transmitter which is transmitting your identity and some information about who I am and where I am. And depending on the, and it goes through different phases. So for 2 minutes I will transmit, and then I'll listen for maybe 10 minutes to see which other station I can hear. And when, so this is actually a chart, a map that's was produced by a radio. So the radio was very similar to this. This is a little software-defined radio, and if we get a chance, I'm going to switch this on later, and we can listen to some of these signals. But it, compared to the massive amount of equipment we had over there, this is an HF radio, and it will operate from 160 meters up to 10 meters. But you can see here, I set it up on the computer, and I'm operating on 20 meters, so 14.0956 megahertz is the setting, and I'm transmitting, in this case I was transmitting 1 watt, which is very low power. And all of these stations are similarly transmitting low power. So we're looking at how good is the propagation on 20 meters at low power. And you can see that probably over 24 hours, these are what we call spots. Somebody receives the signal and then posts it in a log on the internet that everybody has access to. So I can't tell you which of these I was hearing these stations versus them hearing me, but there was definitely good communication right across North America, and that's out to Hawaii, Japan, into Russia, into Europe somewhere, into Russia. So we're getting these pretty good propagation. And 20 meters most of the time is pretty good, especially in daytime. The report up there is the one I'm really proud of. So the amount of power that I'm putting out from this transmitter is about a watt. So here's a flashlight, and I'm guessing that's about a watt of power. So you can imagine that you might see this, maybe if it was on a mountain, you might be able to see it a few kilometers away. But this report was with station DP1POL received my station on this frequency using protocol, and he was almost 16,000 kilometers away, and I think he was either down in Australia or Antarctica on 1 watt, which is it shows the power of the effects of skip, that you can bounce have multiple hops off the ionosphere. So this is some more logging reports. There are sites where people will do this thing called spotting. Every time they make contact, they will log it on a website, and you can look at maps showing who's communicating with whom on the channel. So mentioned here, 20 meters is yellow, so there's a lot of traffic going back and forth between Europe and North America on 20. That's 1510. So this must have been enjoying a good sunspot cycle. There's a lot of 10-meter traffic going this way, less on other bands. So 15 meters, a lot of North America to Africa traffic on 15. So it's interesting to look at these charts to see what the current conditions are, who's able to talk to whom. This chart shows basically worldwide activity on different bands. So the vertical axis is the number of contacts, and the horizontal axis is the distance. So the greatest distance communication here is happening on 30 meters, but it's not a lot of traffic on 30 meters. There's a lot more on 15 meters. 20 meters. Down here at 80 meters, there's some communication going on, but not long distance. So if you want to go long distance, good probability of being able to communicate. We're probably going to work on 20 meters or 15 meters on this particular day, which was when conditions were better than they are now. There are other tools that are used for prediction. So for a long time there was well, there still is, a radio broadcast called Voice of America, VOA, and it was basically the US government, and they wanted to know how well their service was propagating. So they did a huge amount of research that's now available to us in this tool called the VOA propagation tool. And what you can do with this is pull in information about the current solar conditions and look at any specific band and set it up and generate these contours, which are signal strength contours, showing how good the signal will be in any particular area. So we're here in Vancouver, and we're on here. How do you see that? Whatever band we're on, it's showing that we've got a strong SI signal basically across North America, and we can communicate out to maybe this contour line here. So again, if I get a chance, I'll show you this tool in operation. Okay. So I wanted to spend a bit of time looking at some questions that are on the exam, just as sampling questions. Skywave is another name for ionospheric wave. Use those sort of interchangeably. Reception on high-frequency radio waves beyond 4,000 kilometers is generally possible by ionospheric wave is the answer. The cause of the ionosphere, what causes the ionosphere to form? It's solar radiation ionizing the outer atmosphere. When is the ionosphere most ionized? Midday, because that's when it's most intense, just as it is the hottest part of the day. What's the maximum distance along the Earth's surface that is normally covered by one hop in the E region? And that would be 2,000 kilometers. Two or more parts of the radio wave follow different paths during propagation may result in phase difference at the receiver. This change at the receiver is called fading, where sometimes it's good, sometimes it's bad. The usual effect of ionospheric storms is to cause a fade out of the skywave signals. So during the storm, we're losing the ability of propagating by skywave, that period where the HF band was completely dead. The terminology we often use to describe whether a band is usable or not, we describe it as either being open or closed. If it's open, then it's good for communication. If it's closed, then it's useless. And that depends on the level of ionization. What else have we got here? What is the solar flux index? It's a measure of the solar activity taken at a specific frequency. So it's a measure of that electromagnetic radiation from the sun at, I'm not sure what the frequency is, but it's probably ultraviolet frequency. Which two types of radiation from the sun influence propagation? The electromagnetic radiation and the particle emission, so the flares causing we get electromagnetic radiation all the time because the sun is glowing, but there are times where it's more intense, and there are these coronal mass projections that cause particles to be emitted. The ability of the ionosphere to reflect high-frequency radio signals depends on the amount of solar radiation.